Okay, we're looking at question number 4, and this is with no calculator. So looking at this, we are given the graph of f, okay? And we are told that f be the function given such that f of x equals the natural log of x times the sine of x. Okay, so I'm just clarifying the facts given to me. There we go. Next, the figure above shows the graph of f between 0 and 2 pi. So we've got 0 and then we've got 2 pi here. Great. The function g is defined such that g of x is the integral of 1 of x to f of t. Well, that's interesting. Then just to clarify things then, if we take the derivative of g of x, then we know by the fundamental theorem, then the derivative of g of x will be equal to f of x. So something that will help us understand this problem even better is not only is this the graph of f, but this is also the graph of g prime x. Great. Now, letter A. The question says find g of 1 and find g prime of 1. Okay, so g of 1. So I'm going to take the value 1 and substitute it into the g function, which will be 1 to 1 of f of t dt. Sorry for my writing here, folks. Now we know that if the limits, lower limit and upper limit, are the same, then that is always equal to the value of 0. So therefore we know that g of 1 equals 0. Now this is probably a fact I'll be using, so I'm going to label it up here. G of 1 equals 0. Now we need to find what is the slope. So g prime at 1. Well, we know that g prime is f of x, so we want to find what is the value of natural log of 1 times sine of 1. Okay? So we're looking at this graph actually here. So g prime of 1 then will be equal to this function. So if I look at the graph then, at 1, we see that the y value is 0. So g prime of 1 is 0. Now I just proved that looking at the graph, but algebraically we know that the natural log of 1, in other words e to what power is 1? Well, we know that to be 0. So we have 0 times sine of 1, which is 0. So we can prove it algebraically and graphically. Great, now let's move on to part B. Okay, so I'm going to erase this, give myself some more space here. Okay, so part B says, on what intervals, if any, is g increasing? Well, in order to decide whether a function is increasing, we look at its derivative, right? So we want to look at the derivative of g and see when is it positive. So this graph is the graph of the derivative of g. And we notice that in this interval here, g prime of x is positive. So therefore, g is increasing. It looks like it's between 1 and pi. But how could we verify those zeros? Well, we look at the function f of x, which is the natural log of x times sine of x. And if I set that function equal to 0, then I can determine exactly what those zeros are. Graphically, it looks like it is at 1 and at pi, but we're going to verify that. So here we've got a product is equal to 0, so then by the zero product property, we can set each factor equal to 0. So natural log of x equal to 0 and sine of x equal to 0. Well, natural log of x will be equal to 0, so it's e to the 0 power is 1. So x equals 1. Now sine of x equals 0, so we know that that occurs at either 0 or pi. Now since we're started at 0, then in this situation, x would be pi. So therefore the zeros occur at 1 and at pi. Okay, so to answer the question, when is this function increasing? Well, it is increasing between the intervals of 1 and pi, since that is when f of x is greater than 0. Okay, now moving on to part B. So part B says we're looking at between 0 and 2 pi, find the value at which we have an absolute minimum. Justify your answer. Well, we know that minimums occur at critical points or at endpoints. Did you remember that? Okay, now let's answer part C. So part C, we had to find the absolute minimum. Now, I don't know if you remember, but absolute minimums occur at critical points and they occur at endpoints. Okay, so a minimum will occur when the slope is changing from a negative to a positive. So we see that that occurs right here when x is 1. Now the endpoint, a possible absolute minimum, would also be here at 2 pi, because we notice that the slope is negative. So if the slope is negative, then the endpoint, right, because if you're decreasing, then the endpoint will be a minimum. So we have possible endpoints when x is 1 or when x is 2 pi. Now we know from when we did our work in letter A that g of 1 has a value of 0. Okay, now what we need to do is we need to compare the areas from 1 to 2 pi to see which area has the greater value, or in this case would be the absolute minimum. The greater area is below the x-axis. So when I compare from 1 to pi of f of t, and then if I look at the integral here from pi to 2 pi of f of t dt, we're noticing that this area here is greater than that of the first portion. And so then what would result then, since it's a negative value, then I would be moving more to the left, or if that was velocity, but the value would be more negative. So then by comparing areas, I can say that 2 pi has the absolute minimum. And last of all, part D, is there a value of x at which the graph g is tangent to the x-axis? Explain why and why not. Well, in order for a graph to be tangent to the x-axis, what needs to happen is that you have to have the same slope. So the x-axis, the slope is 0, and it has to touch the x-axis. So that means then the y value must be 0. Okay, so we want to find out then when is g prime of x equal to 0 and where is g of x equal to 0. Well, we know that at 1, g of 1 is equal to 0, and we know that the slope at 1 is also equal to 0. So therefore, yes, the graph of g is tangent to the x-axis at x equals 1. There you go.